Hello class, this is Dr. Hilton. This is part 3 of chapter 2. The last time we were talking about chapter 2, we finished with polar covalent bonds. Remember, with polar covalent bonds, the electrons or the atoms are sharing electrons, but they are not sharing them equally. Whereas with a non-polar covalent bond, the atoms are sharing electrons and they are sharing them equally. So water is a polar molecule. The two covalent bonds in water are both polar. And because of that, it can make a new type of bond called a hydrogen bond. A hydrogen bond is individually a weak attraction, but there tends to be lots of them when they're involved, and they do add up. So they can be a force when making matter. It's typically going to be opposites attracting, so hydrogen atoms in a polar covalent bond are typically going to be slightly positively charged, and we'll look at water in a second and I'll remind you why. And then an electronegative atom like oxygen or nitrogen are going to be slightly negatively charged, and those opposite slight charges will attract. Typically it's associated with water, a hydrogen bond. It's also typically between different molecules. But when you get to proteins, there's hydrogen bonds in proteins. A lot of times those hydrogen bonds are within the molecule. And another example is DNA. DNA is double-stranded, and the two strands are held together by many hydrogen bonds. So that is between molecules, technically. So let's look at some visuals. So here are three different representations, three different models of water. And these two electrons here are the ones being shared between this oxygen and this hydrogen for this group. But also these two are shared between this hydrogen and our oxygen. Because oxygen is very electronegative and hydrogen is electropositive, remember our electrons orbit around oxygen a little bit more than the hydrogen. So it's sort of the 2 for me, 1 for you, 3 for me, 1 for you, and this happens with both hydrogens. So you get the electrons spending a lot more time around the oxygen than the hydrogen. So the oxygen is partially negative, and the hydrogens are partially positive for both of them. And the symbol I'm writing, you can see it in the textbook. It's a lowercase Greek delta, just meaning there's a change. So there's a charge difference. So every place where you see red here, that's a partial negative. And everywhere you see white, that's partially positive. because the whites are the hydrogens and the reds are the oxygens. And they can align. You can see this dotted line here. Covalent bonds are typically represented by lines. You can't really see that. Covalent bonds are typically represented by solid lines, ionic by dashes, and hydrogen bonds by dots. But it'll always be between an oxygen and a hydrogen. And you can get lots of hydrogen bonding within water. And that's why you get surface tension. And if you've ever belly flopped, you have felt surface tension. If you've ever seen a bug walking on water, you've seen surface tension. It is a force due to these hydrogen bonds. It hurts when you belly flop because of these hydrogen bonds. Water is attracted to itself, and it's due to these hydrogen bonds. And the hydrogen bonds only form because of the polar covalent bonds, due to the opposite charges. These hydrogen bonds give water some superpowers. One of them is that water has a high heat capacity, meaning it can absorb lots of heat. So water will rise in temperature slowly, and it will cool slowly. It will heat up slowly and cool slowly. So if you look at coastal areas, a lot of times they're more temperate because in the summer the water cools the area because it is cooling slower than the land. And then during the winter it will warm the area because it's a delayed reaction. It's still warm from the summer. Another reason this is important, because it has a high heat capacity, it has a high heat of vaporization, which means when water evaporates, the hottest water molecules leave, and that transfer of heat from liquid water to gaseous water cools down the water that remains. And that's how sweat works. So when a sweat droplet forms on your skin and it's getting and it's heating up due to your body, the hottest water molecules in that sweat droplet will leave as water vapor, and that cools the rest of the water that's still attached to your skin. And the only way that works is if water can leave, if water can evaporate. Water evaporation is dependent on how much moisture is in the air. So this is why when there's lots of humidity, it's really hard to cool down. And you sweat, but you don't feel cooler. That's because your sweat isn't working. Due to the large amounts of humidity, the large amounts of water in the air, the water won't leave your skin as water vapor, and so the water on your skin can't cool down. So that's what I was talking about. The next superpower, water, is a great solvent. Water can dissolve anything polar. It can dissolve anything with a charge, ionic. The only thing it can't dissolve are things that are hydrophobic. Hydro here means water, and phobic comes from phobia, which is a fear. Certain substances do fear water. You've seen oil and water separating in like Italian salad dressing. So it's typically fatty substances that don't mix with water, but there's a few others as well. The properties of hydrophobic molecules is that they're often non-polar. So non-polar things tend to be hydrophobic, and they don't mix with water. If things are polar, they do mix with water, and they're considered hydrophilic. Hydro again is water. Philia comes from Aphrodite, and it means love. So water-loving molecules are hydrophilic, and that includes anything that's polar and anything that's ionic. Both will dissolve in water. A solution is a mixture of a solvent, which is often water, and solutes. Solutes are things that get dissolved in water. My favorite example is Kool-Aid, because almost everyone's made Kool-Aid. In order to make Kool-Aid, you have your powder within your packet, and then you add water to dilute. Your Kool-Aid powder is your solute, and your water is your solvent. When you first add your Kool-Aid packet to your water, you can see the powder, but over time, as you stir it, you get rid of almost all of the particles, and you've made a solution. So the solution is the actual Kool-Aid that you drink. It has both the solvent, the water, and the solute, the Kool-Aid powder, the sugar and the flavoring. Now I said water will dissolve anything polar. It'll also dissolve anything ionic, like a salt. Remember, table salt was sodium chloride. And opposites will attract. Water will pull apart sodium chloride crystals and solvate them by orienting according to its charge. So sodium is positively charged, opposites attract, so the partial negative of the oxygen will be closer to the sodium. On the other hand, chlorine is negative, so it associates with the partially positive hydrogens, so they are closer to the chlorine anion. So that orientation is based on the charge of the atom. One of the other superpowers of water are the properties of cohesion and adhesion. Co means with or together. It's water's ability to stick to itself. And that property is what gives us surface tension. But if you've ever put a straw in a glass of water or a soda or any sort of drink, really, if it's mostly water, the water level in the straw will be a little higher than what's in the glass. You've also probably seen, like when you have a small puddle of liquid on a counter, and then you just stick the edge of the paper towel in that puddle, and the paper towel seems to soak it up. Both of these properties are due to adhesion. Ad means to or toward, and it's water's ability to cling to something else that is polar. So cohesion is water sticking to itself. Adhesion is water sticking to something else that's polar. And water will crawl up tubes, and that's known as capillary action. And the way paper towels work is they have lots of small diameter tubes or tunnels within that paper. And each of these holes gets filled with water due to capillary action. This is also how water gets from the roots of a tree up to the leaves. That is because the tissues in the tree basically make a bunch of very small tubes. They are the width of a cell. So they are very small, and water can travel up the tree against gravity due to this capillary action, which is due to the cohesion and adhesion properties of water. One of the last superpowers of water is that ice is less dense than liquid water. And this is one of the few things, the few substances on Earth that is less dense as a solid. Most things, when you convert them to a solid, they become more dense, but water actually becomes less dense. And that means that ice floats. So if you look at lakes or streams, those bodies of water will freeze from the top down. When they freeze from the top down, that top layer of ice behaves like an insulator, and the water underneath that ice stays warmer and does not freeze. If ice sank, those bodies of water would freeze from the bottom up. There would be no insulation, so there would constantly be liquid water exposed to the cold air, which would create more ice. That ice would sink and fill up, and the entire body of water would freeze. With the ice floating and freezing top down, that insulation keeps some of the pool or stream or pond liquid, so that organisms in the water can stay alive. And basically that's because the length of the hydrogen bond in water is variable, because in liquids molecules get to move around more, they're more active, so the hydrogen bond length is changing and variable in water, and if you take the average length, it's actually shorter due to these collisions. But if you look at solid water, the length of the hydrogen bond standardizes because those molecules are moving around less. The hydrogen bond length will stabilize. As an average, they get longer, so there's more space between the water molecules. And therefore, with more space, it's less dense.